Okay, folks, I want to go through the proof of Fermat's theorem. Remember that Fermat's theorem said, suppose x equals c is a local extrema. Remember that word extrema means a max or a min. Local max or a local min. By the way, when I do the proof, I'm going to only do it for a local max. If you'd like to do the proof for a local min, you will just switch the initial inequalities that we have set up. So suppose we've got a local max or a local min at x equals c, then if f prime of c exists, if it's differentiable at c, if we're able to take the derivative at x equals c, then f prime of c must equal 0. Okay. There should be something a little bit intuitive about this. If I take some function here, let's call it f, notice that f has a local maximum right here at x equals c. Okay. If I were to, if it's differentiable at x equals c, then the derivative must be what? Must be 0. We have to have a horizontal tangent line there. Okay. So this part guarantees that it's differentiable, and we're going to see that that is going to guarantee that that derivative is 0. Let's just show where Fermat's theorem breaks down. Let's suppose this is our function, f. Then notice at x equals c, the derivative doesn't exist, so the derivative doesn't equal 0. And that should sort of make sense. You can't draw a tangent line slope here, or there is one. It's a vertical tangent line, but there is no that derivative does not exist. Therefore, it can't be 0. Okay, so let's go ahead and do the proof. Oops, I don't know what just happened there. Let's go ahead and do the proof. And remember, in this proof, I'm assuming that C is a local max. Okay. So remember that when we say that f of C is a local max, that means there's an interval I there's a way to draw a neighborhood around C so that f of C is greater than or equal to f of x for all x coming from that interval. So that can be somewhat weighty notation. Let's go ahead and just look at the picture of that and see what I'm saying here. So if here's our function, oops, it's just f of x. Okay. Notice that at c, we've got a local max. That means that we can construct this interval around c so that picking any x value, let's say we pick this one right here, any x value and plugging it into the functional value at f of x will be below the functional value at f of c. So here's f of c, and here is f of x. Okay. So that's just reiterating the definition of what it means to be a local maximum. And I'm going to take that interval I. I need that interval I to be able to do this problem. Okay. So what we're going to do is we're going to set the value h equal to x minus c. Okay. So if this were our chosen x value, then h is going to be this distance right here, the distance between the two. So h is equal to x minus c. Notice that this says that if I solve this for x, we have that h plus c is equal to x, or put it another way, x would be equal to c plus h. So we're going to sometimes write it that way. Okay. So we're now going to break this into two cases. If x is to the right of c, as it is in my picture here, then h, which is equal to x minus c, well, if x is larger than c, then this difference right here is always greater than 0. Okay, so that's the first case. So then go back to the definition of a local maximum. We said that f of c has to be greater than or equal to f of x. So this y value has to be bigger than this y value. So f of c is greater than f of x. Okay. That means that f of c, though, is greater than f of c plus h. Because remember, we said h was x minus c, meaning that x was c plus h. Okay, so right now we've got that f of c is greater than or equal to f of c plus h. So let's go ahead and take this expression and then subtract f of c plus h over to the other side. So we have f of c is greater than or equal to f of c plus h. And we're going to subtract this f of c over to the other side, so we get that 0 is greater than or equal to f of c plus h minus f of c. Okay. Maybe you see where we're going here. I'm starting to build on this side the limit definition of the derivative. So what should we do? We should divide both sides by h. Now, can I do that? Well, by the way we chose to define h, it was an x value. It had to do with the distance between c and an x value. H is always positive in this case, and specifically h is non-zero, so I can divide both sides by h. Okay? So we've got that 0 is greater than or equal to f of c plus h minus f of c all over h. Notice that this is not yet the derivative because we haven't taken the limit yet. So let's go ahead and take the limit as h approaches 0 of both sides. And I'll make a comment about that limit in just a second. Remember, when we take a limit, we're saying we can approach 0 from either direction, either the positive direction or the negative direction. But here we made an assumption. Remember, we're still in this case 1. And in case 1, we said that x was to the right of c, meaning that h had to be positive. So this limit does not necessarily apply here. I'm going to look at just the limit as we approach 0 from the positive direction. So this gives us that 0 is greater than or equal to the limit as h approaches 0 from the right of f of c plus h minus f of c all over h. Why was this limit 0 here? Because we were taking the limit of a constant, and the limit of a constant is just that constant value. So let's look at what we've just said. We've just said that 0 is greater than or equal to f prime of c. In all of these cases, I should have put provided the limit exists, because we took a limit of both sides without necessarily knowing that that limit exists. Okay. So we have that 0 is greater than or equal to the derivative at c, provided f prime of c exists. So if it's differentiable at c, then that derivative is going to be greater than or equal to 0. That was case 1. Now let's look at case 2. We have x values that are also to the left of c on this interval, okay, which if we pick those x values, we have x less than c. But that means that h, which is equal to x minus c, if the x values are smaller than the c values, then that means that h will always be less than 0. Okay? So we're going to repeat the construction from before. Even though x is now to the left of c, we still have that f of c is greater than or equal to f of x, which means that f of c is greater than or equal to f of c plus h. I'm still going to subtract the f of c over to the other side, so we still get this expression here. Now what would I like to do? Now what I'd like to do is again divide both sides by h. But when I do so, when I divide both sides of this inequality by h, what do we know about h? Unlike in the first case, where h was positive, here we have that h is negative. And what happens when you divide an inequality by a negative number? You reverse the direction of the inequality. Get up there so you can see that. So this gives us that 0 is less than or equal to f of c plus h minus f of c all over h. I'm now again going to take the limit as h approaches 0. I'll comment on that, of 0. That's going to be less than or equal to the limit as h approaches 0 of f of c plus h minus f of c all over h. Again, this is provided the limit exists. But in this case, what did we say about our h values? Well, in case 2, the h values are always negative. And so we can only approach 0 from the left-hand side here. So this gives us that 0 is less than or equal to the limit, as h approaches 0 from the left, of f of c plus h minus f of c all over h, again, provided the limit exists. So that tells us that 0 is less than or equal to f prime of c, provided the limit exists, or provided, let's say it like this, let's say provided c prime, f prime of c exists. Well, let's look what we've said in these two cases. So we examined the two cases, and both cases hold. So in case 1, we said we eventually got down to the point that f prime of c had to be less than or equal to 0. And in case 2, we said f prime of c had to be greater than or equal to 0. Well, if both these cases hold, because we can pick x values on either side of that interval, okay, then we have f prime of c must equal 0. Because if numbers less than or equal to 0, greater than or equal to 0, then that number actually must be 0. So let's just go back up to the original statement of Fermat's theorem. We said if we have a local extremum at x equals c, and if that derivative exists, then that derivative must be 0. Here's the picture that goes with that proof, and we did the work to show that yes, indeed, f prime of c was 0.